How do you program with CUDA? If you are curious about how to program with CUDA, you are in for an exciting journey into the world of graphics processing units. CUDA, developed by NVIDIA, is a platform that allows you to harness the power of graphics processing units for general-purpose computing. Let's break down how you can get started with this innovative technology. First, you need to understand that CUDA extends standard C and C++. It adds special features and application programming interfaces that let you write code that runs directly on the graphics processing unit hardware. This is essential for tasks that requiring high performance and parallel computing. Now, what does programming with CUDA look like? It introduces the concept of heterogeneous computing. In this setup, you have a central processing unit, known as the host, and a graphics processing unit, referred to as the device. Each has its own memory space, and you must manage the data transfer between them. The central processing unit handles tasks in a serial manner, while the graphics processing unit excels at parallel workloads. When writing a CUDA program, you will use C or C++ with some added keywords. One of the key concepts is the kernel, which is a function that runs on the graphics processing unit. You mark these functions with the special keyword global. To launch a kernel from the central processing unit, you use a unique syntax that specifies how many parallel threads will execute the kernel. The typical workflow for a CUDA program involves several steps. First, you allocate memory on the graphics processing unit. This memory is separate from that of the central processing unit and must be managed carefully. Next, you copy the data from the central processing unit to the graphics processing unit. This step is crucial because the graphics processing unit cannot access the central processing unit's memory directly. After that, you configure the kernel launch by specifying the number of threads and how they are organized into blocks and grids. Then, you launch the kernel, allowing the graphics processing unit to execute it in parallel across many threads. Once the kernel has finished executing, you synchronize the central processing unit to wait for the graphics processing unit to complete its tasks. Finally, you copy the results back from the graphics processing unit to the central processing unit for further use. To give you an idea of what a simple CUDA program looks like, consider this example. You might write a kernel function called hello that prints a message from the graphics processing unit. In the main function, you would launch this kernel with a specific number of blocks and threads, and then synchronize the device to ensure the central processing unit waits for the graphics processing unit to finish. CUDA is widely used in various fields that requiring heavy parallel computation, such as scientific simulations, machine learning, and image processing. Its ability to process large datasets quickly makes it a popular choice for tasks that would be too slow on a central processing unit alone. While CUDA itself is not a domain-specific language, it often serves as a target for domain-specific languages that generate graphics processing unit code. For instance, high-level libraries in Python or MATLAB can utilize CUDA to speed up computations without requiring the user to write low-level graphics processing unit code. This makes GPU computing more accessible to a broader range of developers. In the context of emerging technology, CUDA represents a shift toward systems that combine central processing units and graphics processing units for optimal performance. As graphics processing unit hardware continues to improve and programming tools become more user-friendly, CUDA is likely to play an increasingly important role in software development, especially in areas that requiring real-time processing or handle vast amounts of data.